In the year 1600, Johannes Kepler attempted to map the orbit of Mars. He utilized traditional Copernican circular models and applied them against the unprecedented observational data recorded by astronomer Tycho Brahe. After extensive adjustments, Kepler reached the limit of the circular model. His best possible orbital calculation left a microscopic discrepancy between the predicted path and the raw data, exactly 8 minutes of arc. Standard scientific practice of the era dictated that a gap of this size should be ignored. Astronomers regularly dismissed such minor variations as an acceptable margin of observational error, or temporarily patched them with ad hoc mathematical assumptions. Kepler refused to ignore the data. He identified the tiny gap as a definitive structural signal. To resolve it, he collapsed the prevailing reliance on perfect circular geometry entirely, introducing elliptical eccentricity as the vital term needed to close the equation. This historical pivot forms the core premise of the theory of infinity, or TOI. TOI is an ontological framework that categorizes structural phenomena by carving them out of a totality, treating anomalies as critical boundary markers. Under TOI, mathematical gaps are positive correlation signatures called beta phenomenal effects. They demand the addition of a new, conserved term to maintain structural harmony. Tracking and interpreting these systemic gaps is now a formalized mathematical procedure known as the residual audit. Engineering a seamless transition between distinct spatial dimensions requires absolute precision. We have to actively hunt for these geometric residuals and integrate them into the architecture rather than discarding them as noise. When a mathematical model encounters a structural residual it cannot absorb, the geometric boundaries of that model experience a systemic failure. The internal laws governing the shape break down. Under the TOI framework, this specific point of failure is known as not infinity. Not infinity is strictly a topological boundary event. It is the precise moment an operation attempts to extend a structure beyond its operational limits. It is not a quantitative endpoint or a number. We see the physical equivalent of a not infinity event when a continuous, undulating spatial dimension is forced into a rigid Cartesian volume. The geometric typing of the continuous wave collapses upon hitting the discrete grid. Surviving this dimensional collapse requires a complete departure from ad hoc theoretical patching. We must adopt a unified, fundamental topological ontology that anticipates the failure and safely reroutes the mathematical tension. To build a rigorous cross-domain transport system, we rely on the TOI invariant alphabet. This system operates from absolute zero assumptions, bypassing the paradoxes of creation from nothing by defining elements that stand a priori to any formal mathematical structure. The first element is the unknowable unknown, designated as psi. Psi represents the unstructured, turbulent background potential medium, a carrier field completely devoid of established form. To extract structure, we apply the symmetry operator, phi. This highly tuned filter channels the turbulent psi field into organized geometric regimes. The output is a sealed mathematical world, classified as a golden set, or theta. Inside this enclosed golden set, a computational model known as the Amanda root engine actively maintains the boundary. It runs continuous cybernetic audits, called fate checks, to monitor structural integrity and ensure the background potential remains neutralized. Establishing this firmly sealed golden set is an absolute prerequisite. Only when the topological boundaries are locked can complex biological or continuous data be transported across dimensions without fragmenting. The primary engineering challenge of the quantum adapter is data preservation. How do we pull a continuous spatial surface through these boundary operators without triggering a catastrophic breakdown in its representation? The master orthogonal filter dictates dimensional transport via two parameters.
Symmetrically, when A equals B, the Turing surface seals perfectly at a 1-to-1 ratio. But if we stretch A to the golden square and shrink B, gauge invariance is a property where a system's internal measurements remain perfectly unchanged despite underlying transformations to the spatial field. Because the volumetric payload evaluates identically before and after the distortion, the continuous spatial surface demonstrates total immunity to extreme golden scaling. Proving gauge invariance is the mechanism that allows the adapter to function. Highly complex topological phenomena can be stretched, compressed, and transported across completely different bounded contexts with absolute zero information loss. We can map these spatial mathematics directly onto their continuous physical counterparts, biological reaction diffusion fields. Reaction diffusion fields are continuous models that describe how chemicals interact and spread, generating boundary bands recognizable as tiger stripes. Artifact 3 applies a rigorous spatial frequency acceleration to this continuous morphogenetic field, driving the operational frequency from the standard golden ratio up to the golden square. This chart plots the cumulative mass evolution of Turing fields. The upper blue line shows the baseline field accumulating mass toward 4.0. By squaring the phase inhibitor, we biologically clamp the accelerated field, the magenta line, stabilizing its mass exactly at 3.057. Dynamically clamping the continuous biological shape lowers its total volume. This restriction inversely prepares the geometric mass to safely interface with rigid, discrete scaling laws without immediately shattering the boundary. The final cross-domain transport phase forces this clamped biological Turing mass out of its continuous state and maps it into a strict, rigid Cartesian volume. We execute a specific arithmetic projection. The system takes the periodic 8-fold space and divides it by the exact physical mass of the continuous stripes, which we established at 3.057. The target for this projection is the fundamental discrete golden area rail, evaluated at 2.618. Passing this through the residual suite reveals the observed value lands at 2.616. This slight gap from the golden rail is quantified as an absolute logarithmic residual of 0.0528. Under TOI protocols, this 0.0528 residual is not a calculation error. It is the literal quantified measurement of topological friction generated when organic biological domains are forced to map onto rigid computational matrices. This exact mathematical friction is the breaking point that destroys lesser models. It proves definitively that continuous spatial shapes can never map perfectly onto discrete grids without generating structural tension. The seamless quantum adapter solves this crisis. It is not designed to force a perfect fit where one is mathematically impossible. Rather, it operates as a highly complex adjacency operator that manages the inevitable friction. At the precise boundary of the golden set, the adapter employs a cybernetic mechanism known as the J13 valve of tension. The J13 valve actively regulates the permeability between adjacent dimensional loops. Instead of discarding the 0.0528 residual gap as noise and triggering a not infinity collapse, the adapter utilizes the J13 valve to actively siphon off that discrepancy into a latent tension reservoir. By isolating this residual energy, the adapter ensures compliance with the J14 global invariant rule. The global energy of the system remains strictly conserved and balanced, even when the local transitions between realities are mathematically mismatched. The quantum adapter pairs exact gauge invariants to asymmetrically stretch the spatial manifold, with cybernetic tension routing to capture the resulting geometric friction. By securing both ends of the transport ledger, the continuous cosmos is cleanly integrated into a discrete algorithmic machine.